The Geological History of Iowa, prepared by the Iowa Geological and Water Survey with assistance from the Iowa Limestone Producers Association. The Paleozoic era, from 542 to 251 million years ago. Following the Precambrian Eon, the most recent 542 million years of geologic time is called the Phanerozoic Eon. Looking a little more closely, the Phanerozoic is subdivided into three eras: the Paleozoic, the Mesozoic, and the Cenozoic. We will examine each of these eras individually, beginning with the Paleozoic, the oldest of the three. It includes a period of 291 million years between 542 and 251 million years ago. The Paleozoic, or early life, comprises about 6.3% of the Earth's geologic history. The Paleozoic era itself is subdivided into a series of periods with names that are a little more familiar to most people. The oldest is the Cambrian, from 542 to 448 million years ago. Then the Ordovician, 448 to 444 million years ago. The Silurian, 444 to 416 million years. The Devonian, from 416 to 358 million years. The Mississippian, 358 to 325 million years ago. The Pennsylvanian, 325 to 299 million years ago. And finally, the youngest period, the Permian, from 299 to 251 million years ago. Some of the most important events of the Paleozoic began with the Cambrian explosion, when most of the major lineages of animals on Earth evolved. The first vertebrates appeared late in the Cambrian, about 500 million years ago. Plants moved onto the land in the Middle Ordovician about 450 million years ago. The first jawed fish evolved in the Middle Silurian 420 million years ago, followed by the first insects about 400 million years ago. Vertebrates moved out of the sea and onto the land, and plants evolved to produce seeds near the end of the Devonian about 360 million years ago. The first reptiles evolved in the Pennsylvanian about 315 million years ago, and the Earth's continents were gathered together to produce the last supercontinent, Pangaea, about 300 million years ago. Finally, the Paleozoic ended with the greatest known mass extinction of life on the geologic record, the end Permian extinction. Rocks of all Paleozoic ages, except the Permian, are known from Iowa. Although some rocks of that age were surely deposited in the state, they have apparently all been lost to erosion. There are many methods of portraying the continents on Earth. The most accurate is to use a globe, but only one side of a globe is visible at any given time. A type of map that accurately shows the entire Earth in one view is called a Mollweide projection. Think of a world globe that was split from North Pole to South Pole, then pulled open and flattened out. This is a Mollweide projection of the Earth today. We'll use this projection to show you the distribution and movement of the continents on the Earth through the 269 million years of the Paleozoic. Plate tectonics is the mechanism by which the Earth's continents move around the planet's surface on a series of ever-changing plates. The plate tectonic process was discussed in more detail during our presentation of the Precambrian of Iowa. The Earth's plates have been spreading apart, subducting under, and sliding past each other for about 2 billion years, continuously changing the configuration and locations of the continental land masses. About 6 times, all of the continental crustal fragments have been grouped together as a single supercontinent. One of these supercontinental groupings, called Rodinia, formed late in the Precambrian about 1 billion years ago. Rodinia moved down to the South Pole and began to break up about 750 million years ago. By about 600 million years ago, it looked something like this, with the area that is now the United States outlined in red, and Iowa located by the red asterisk, not too far from the South Pole. This set the stage for the beginning of the Paleozoic. By the beginning of the Paleozoic, Rodinia had split into two major continents. Early in the Cambrian, about 520 million years ago, North America, including a large portion of the U.S., Baltica, and Siberia were part of one continent called Laurasia, and Iowa lay well south of the equator. The southeastern portion of the U.S. had not yet been joined to the rest of North America. It was a part of a much larger continent, including all or parts of what are now Antarctica, Australia, Africa, and South America. The Iapetus Ocean that separated Laurasia and Gondwana was opening, with Laurasia being pushed north toward the equator. Iowa's location near the center of the North American landmass meant that rocks were being eroded from that region, and Cambrian sediments would not be deposited until the seas pushed into central North America later in the Cambrian. Later in the Cambrian, about 500 million years ago, the Iapetus Ocean continued to expand and Laurasia continued to drift north, with Baltica rifting and moving away from North America. The seas had advanced out over portions of the continent, including much of North America, inundating the area that is now Iowa. This transgression of the seas resulted in the deposition of the oldest Paleozoic sedimentary rocks in Iowa, sequences of sandstone and limestone. By Middle Ordovician time, about 450 million years ago, Gondwana was slowly rotating and moving further south. Laurasia and Iowa had begun slow counterclockwise rotation, and Siberia had broken free, moving north of the equator and opening the Paleotethys Ocean. The southern portions of Baltica rifted off and joined with a series of new volcanic islands to form the microcontinent of Avalonia. Iowa still lay beneath shallow seas just south of the exposed Laurentian land. The Iapetus Ocean was closing by the Middle Silurian about 430 million years ago as Gondwana continued its slow rotation. The ocean between Baltica and North America had closed, and the two landmasses began to collide, an event known as a Caledonian orogeny, which pushed up the Caledonian Mountains. The Avalonia microcontinent had moved northward and was itself colliding with southern Baltica. The northern drift of Gondwana had isolated the eastern end of the Iapetus Ocean, creating the Rheic Ocean. Iowa lay beneath a shallow ocean basin that covered much of the south-central part of Laurasia, and a hot, dry climate encouraged the deposition of carbonate rocks. Late in the Devonian, about 370 million years ago, Baltica was welded to North America, and Avalonia was beginning to plow into the continent, an event called the Acadian orogeny that was pushing up the Acadian Mountains, a southern extension of the Caledonides. The Iapetus and Rheic Ocean between Laurasia and Gondwana continued to shrink as the megacontinents moved toward a major collision. The seas were retreating from Iowa, and it would soon be emergent, beginning a period of sediment erosion. During the Mississippian, about 340 million years ago, the Iapetus Ocean continued to close as Gondwana began to collide with Laurasia. This was the Appalachian orogeny, which produced the Appalachian Mountains and pushed Laurasia northward and Iowa toward the equator. Iowa was once again submerged beneath a shallow In the Pennsylvanian, about 300 million years ago, the Iapetus Ocean was nearly gone as a Ouachita orogeny recorded the collision of western Gondwana and southern Laurasia. The Ouachita Mountains developed west from the southern Appalachians, creating a continuous chain of mountains that nearly crossed the merged continents. This marked the completion of the most recent supercontinent, Pangaea. The eastern remnant of the old Iapetus Ocean and the Paleotethys Sea was nearly landlocked. Iowa was now on the equator, on the edge of an inland sea. Finally, the Paleozoic was almost over during the Permian, about 255 million years ago. Most of the seas had withdrawn from Pangaea, and Iowa was now north of the equator and well away from the shallow epicontinental seas. The end of the Paleozoic was marked by a period of rock erosion in Iowa. Most of the Paleozoic rocks in Iowa were deposited in shallow seas that covered Iowa and much of North America periodically over the 290 million years of the Paleozoic, and a few times during the ages that followed, like here in the Cretaceous. This graph portrays the periods of Iowa's history when these seas covered all or a part of Iowa. The blue colors indicate times when the seas covered Iowa from 100% coverage on the right to 0% coverage on the left. The sediments that would become Paleozoic rocks were deposited in these seas. The brown indicates times when the seas had retreated from Iowa and rocks were being eroded away from the state. The movement of the seas onto the land is called a transgression, the withdrawal of the seas a regression. So one cycle of the seas transgressing into Iowa and then regressing from the state is called a transgression-regression cycle, or a TR cycle. The transgressing and regressing seas deposited layer after layer of sediment in Iowa, separated by periods of erosion and minor structural deformation. These layers of sediment and rock build up, one above the other, like layers on a cake. Geologists often refer to these repetitive layers of rock deposition as layer cake geology. The seas first transgressed into Iowa, depositing Cambrian rocks, then Ordovician strata, Silurian, Devonian, Mississippian, then Pennsylvanian rocks. During the Pennsylvanian, the Forest City Basin developed in the southwest corner of Iowa, and all of the strata was tipped, dipping down from the northeast to the southwest. The erosion that followed leveled the landscape, cutting deepest into the up-tipped rocks in northeast Iowa. This produced a distribution of Paleozoic rocks that we see today, the oldest rocks exposed in the northeast, the youngest in the southwest. If we tip this model up, we see the current distribution of Paleozoic rocks at the bedrock surface of Iowa. The oldest, Cambrian, are exposed in the northeast, and the youngest, Pennsylvanian, are exposed in the southwest. Younger still Mesozoic rocks, shown in green and yellow, cover some of the Paleozoic rocks, especially in the northwest area of the state. Most of the Paleozoic rocks in Iowa were deposited in shallow inland seas, called epicontinental seas, that would have looked something like this. A shallow marine environment like this can host the deposition of a variety of sediment types that can be transformed into a variety of rock types, or lithologies. Rivers move sediments from the land to the sea, where the water velocity slowed, allowing the heavier sand particles to drop out near the shore. Farther out, smaller silt and clay-sized particles settled to the seafloor, with only the finest particles making it far from the shore before settling. Sunlight often penetrates deeply into these waters, a region called the photic zone. In the photic zone, sunlight facilitates the growth of plants and animals who deposit calcium carbonate or lime on the seafloor. Nearer the shore, the heavy influx of sediments from the land overwhelms the deposition of the lime. But in deeper waters, farther from shore, less terrestrial sediment reaches the seafloor, and limy sediments dominate. Finally, farthest from the land in the deepest water, sunlight does not reach the seafloor, so no limy sediments are deposited. Only the finest clay particles are able to drift that far from shore, so the seafloor is covered with a fine black mud. Time and geologic processes convert the sediments deposited in these epicontinental seas to sandstone, siltstone, mudstone, limestone, and shale. Now we'll take a closer look at the Paleozoic rocks in Iowa, from the oldest Cambrian to the youngest Pennsylvanian. Early in the Cambrian, during the Cambrian explosion, life was proliferating in other areas of the world. Here we see an illustration of a stromatolite reef based on fossils from the Burgess Shale of central Canada. The stromatolites are the tall, rocky pillars in the background, created by algal mats. The strange creature in the upper left center is Anomalocaris canadensis. It's chasing three trilobites called Paradoxites, seen in the lower right center of the picture. Scattered about the ocean floor are Witwaxia, looking like fringed ashtrays. Sponges, shown in black and brown, and goblet-shaped archaeocynathids are also present. In Iowa, the Cambrian seas were slowly advancing across the state, and currents were spreading layers of quartz sand derived from the eroding Precambrian terrains to the north. This sandy environment did not provide many habitats for most of the Cambrian explosion life forms, so animals in the Cambrian seas of Iowa were much more limited. In Iowa, Cambrian rocks are colored brown on this bedrock geologic map and are only exposed in the northeast corner of the state along the Mississippi and Upper Iowa rivers and their tributaries. The fossils preserved in these rocks are less diverse and spectacular than those from the Cambrian explosion fauna of the Burgess Shale. Among the most common fossils in Iowa Cambrian rocks are trace fossils. These are not actual preserved remains of living creatures, but evidence or traces of their former presence. Trace fossils include preserved burrows, tracks, and resting locations. Trilobites, a group of extinct arthropods named for their three-segmented body form, are found in Iowa Cambrian rocks, as are early brachiopods, which are marine bivalve mollusks that lived attached to the seafloor. The Cambrian of Iowa is also noted for the extensive sheet sands that cover most of the state. The Jordan sandstone is one of the most extensive of these. Here it's shown exposed just north of Pikes Peak State Park at McGregor. This sandstone is present in the subsurface over all or most of the area shown in purple on this map and serves as a major groundwater aquifer, providing large quantities of high-quality water for municipalities and industries in the darker purple area. The Ordovician, often referred to as the age of cephalopods, includes a period of time between about 488 and 444 million years ago. Only a few lichen, algae, and primitive non-vascular plants lived on the land at that time, but the seas were teeming with many familiar animals. A few of them are numbered in this diorama, including 1. Nautiloid cephalopod, an early squid with long cone-shaped shell. Number 2. Brachiopods. Number 3. Trilobites. Number 4. Corals, colonial in the center and solitary horn corals on the left. Number 5, crinoid, animals often called sea lilies. And number 6, unusual animals called conularids, which have no affinity to any currently living animal. When the Middle Ordovician seas transgressed over much of the area that was the central United States about 460 million years ago, they deposited one of these sand units that became the St. Peter sandstone, one of the most widespread sedimentary units in North America. This map shows the extent of the St. Peter sandstone and a related Winnipeg Formation of the Dakotas in north and west. The sand grains that comprise the St. Peter sandstone were eroded from the rocks of the Transcontinental Arch, the Wisconsin Arch, and the Ozark Uplift. Because of the slow nature of the transgression, the sand grains were extensively tumbled by beach winds and surf until resistant quartz was just about the only mineral grain remaining, and they were very well rounded and all about the same size. There are many exposures of St. Peter sandstone in northeast Iowa, and the unit is mined south of Clayton, shown here by the blue star. At the entrance to the Clayton mine, the St. Peter is overlain by a thin Glenwood shale and the massive dolomites of the Platteville Formation. Sand from the mine is processed and used with hydrofracking fluids in petroleum production. Ordovician rocks are exposed in northeast Iowa, the area shown in pink on the bedrock geologic map of Iowa. The Ordovician limestones and dolomites that formed in the shallow oceans that covered most of the state are extensively quarried for aggregate and building stone. They can also be seen in many road cuts in northeast Iowa, such as this one near Dubuque. And the Ordovician Galena limestone forms the scenic bluffs along the Upper Iowa River in Alameda County. The Silurian period, between 444 and 416 million years ago, saw the evolution of the first true plants. It was during this period that plants moved onto the land along the sea and other waterways. This illustration shows a field of one of these early plants, Cooksonia, on the Silurian landscape. However, the only Silurian rocks preserved in Iowa were deposited in the shallow seas that covered the state during much of that time, and this diorama would be a better depiction of their depositional environment. Many of the same animals that occupied the Ordovician seas of Iowa were around during the Silurian, but they had evolved and diversified. The prime predator in the Silurian seas is not shown on this diorama. They were the Eurypterids, or the sea scorpions, some of which grew to be larger than a man. Some Eurypterid fossils have been found in Iowa. Silurian rocks are exposed in east central Iowa, shown in the reddish purple on the bedrock geologic map. In Iowa, Silurian rocks are almost exclusively carbonates, dolomites and limestones, deposited in the shallow seas that covered the state. The subtropical Silurian seas teemed with life in most areas. Consequently, many Silurian rocks in Iowa are rich in fossils, like these from the Hopkinton Formation, that are loaded with brachiopods. However, others, like the Anamosa member of the Gower Formation, were deposited in environments where the water was hot or salty, conditions not very conducive to animal life, so these rocks contain almost no fossils. All of these carbonate rocks were originally deposited as limestones, but almost all Silurian limestone was converted to dolomite, a process that damaged many of the fossils that they preserved. The process called dolomitization that converts limestone to dolomite by adding magnesium to its crystal structure is not well understood. Most geologists believe that magnesium is concentrated by the evaporation of seawater in shallow areas adjacent to the land. Magnesium ions move downward into the porous limestone and are flushed through the rock by fresh water from the land. This creates conditions that allow some of the calcium, Ca, atoms to be replaced in the calcium carbonate crystals by slightly smaller magnesium, Mg, atoms, producing a rock that is a mixture of calcium and magnesium carbonate, called dolomite. Because of the smaller size of the magnesium atoms, the dolomite crystals in the limestone are slightly smaller than the original calcite crystals, so there is a net 13% increase in the rock's porosity. In Iowa, these voids in the dolomite are usually filled with water, so dolomite beds in the subsurface usually make good aquifers to produce well water. Silurian rocks in some areas of Iowa show how depositional environments can change rapidly over a very short distance, producing rocks with a much different appearance. This cross section illustrates Silurian rocks within about a mile of Palisades-Kepler State Park in Lynn County. There are two principal formations, the Scotch Grove Formation below and the Gower Formation above. Both units were deposited in the shallow seas that covered Iowa during the Silurian. Because the seas were so widespread and shallow, circulation was poor. The limited water circulation and hot tropical temperatures led to extensive evaporation and the density stratification, with dense saline brines settling to the lower areas of the seafloor. In the upper portions of the water column, the seas had a normal salinity and life flourished, building carbonate mounds that kept these areas near sea level. Rocks formed from materials deposited on these mounds are rich in fossils, like this sample of the Brady member of the Gower Formation from Palisades-Kepler Park that displays abundant brachiopods. The waters between the mounds were hypersaline and incapable of supporting animal life. Rocks created from these deposits are almost barren of fossils, like the Anamosa member of the Gower Formation that is quarried at Stone City. These rocks were deposited at the same time, only a few miles from each other, but are dramatically different. They represent different facies of the Gower Formation. Subsequent erosion has lowered the landscape to the blue dashed line. These and other Silurian rocks are quarried extensively in Iowa for aggregate and other uses. At the Martin Marietta Cedar Rapids Quarry, just across the river from Palisades-Kepler State Park in Lynn County, the mound facies of the Brady member of the Gower Formation are quarried. At Stone City in Jones County, the inner mound facies, the Anamosa member of the Gower Formation, is quarried and was formerly mined underground. This rock, known as Anamosa stone, is sold for aggregate and other uses, but is also sold in large quantities as building and facing stone. Silurian dolomites are relatively resistant to erosion and frequently form spectacular cliffs and caves. Many of these areas have been protected as Iowa state parks, including Maquoketa Cave State Park, where you can see an ancient cave that was exposed by erosion, forming a natural arch. Iowa's first state park, Backbone Park in Delaware County, includes spectacular cliffs of Silurian dolomite along the Maquoketa River. Here are some of the state parks in eastern Iowa that feature these Silurian bluffs. The white star shows the location of Stone City, where there were numerous historic Silurian quarries and many old buildings constructed of Silurian dolomite can be seen. Following the Silurian, the Devonian period between 416 and 358 million years ago is known as the Age of Fishes. Although fishes did evolve and radiate greatly during this time, so did many other animals that lived in the shallow seas. The coiled-shelled and straight-shelled cephalopods, 1 and 2 on this illustration, both continued to expand and evolve, as did corals. The top predator in the sea at that time was a giant armored fish known as Dunkleosteus, an arthrodire that grew to the size of a school bus. A model of Dunkleosteus is seen in this photo from the Devonian diorama at the University of Iowa. The medium blue color on the bedrock geologic map of Iowa identifies the Devonian outcrop belt, which primarily follows the Cedar River through the state. Great exposures can be seen at many locations along the outcrop belt, but some of the best can be seen along the shores of Coralville Lake in Johnson County. This image shows the Stainbrook State Geologic Preserve that exposes the State Quarry Formation, as well as the Rapid and Coralville members of the Little Cedar Formation along Highway F-28. A truly marvelous sequence of Devonian rocks was exposed in the emergency spillway of the Coralville Dam in 1993, when floodwaters surged through the spillway, eroding the soil and other materials that covered the rocks. The area became an overnight tourist attraction and was called Devonian Fossil Gorge. A wide variety of spectacular fossils were found in the gorge, including a plate from the top of the skull of one of the large armored fish, Dunkleosteus. This fossil and many others recovered from the gorge are on display at the Corps of Engineers Visitor Center near the dam. A reconstruction of this animal and others that lived in the Devonian seas at the time that the rocks in the fossil gorge were deposited can be seen in a diorama in Iowa Hall in the University of Iowa's Museum of Natural History in Iowa City. In 2008, a second flood tore through the spillway, widening the gorge and exposing new rocks and fossils. Devonian rocks contain some of the most spectacular fossils to be found in Iowa. These are a few of the fossil-rich Devonian rocks that can be seen around Lake Coralville in Johnson County. This slab shows a mass of brachiopods preserved in lime mud. Brachiopods are bivalve mollusks that live attached to the seafloor by a flexible stem and collect food by filter feeding. This is a picture of modern-day brachiopods. There was a great variety of brachiopod species in the Devonian, many more than today. This illustration shows a few of the Devonian brachiopod species that can be found in Iowa. One of the most obvious are these spirifers with wing-like appendages. Here's a spirifer preserved in this slab. This slab displays a greater variety of fossils. Lots of brachiopods, yellow arrows, but also the columnar segments of crinoids, orange arrows, often called sea lilies. They weren't really plants, but they're animals that lived attached to the seafloor and moved their arms in the water to produce currents that carried food to their mouth. The white arrows show fragments of corals, similar to modern-day branching corals. Finally, here's a close-up view of a large colonial coral called Billingseye. A separate coral animal lived in each of the circular depressions, which were originally holes. A similar coral can be seen in the lower right of this photo from Devonian diorama in Iowa Hall in the University of Iowa's Museum of Natural History. A coiled-shelled cephalopod can be seen above the colonial coral, and a field of solitary corals with their yellow tentacles behind. Devonian limestones are produced in many quarries in eastern Iowa. Geologists have identified limestones that were originally deposited in a variety of shallow marine environments. The fine-grained limestones in the boulders in the foreground of this quarry were deposited as lime mud. In other areas of the quarry, reef-like concentrations of corals and other fossils are seen, and in others, rocks that were lime sand can be found. The depositional origins of the various limestone layers affect the rock's character and is one of the factors that determines the quality and use of the stone that is quarried. Devonian limestone is also quarried to make Portland cement in Mason City and in Davenport, Iowa. Cement is made by crushing limestone, then mixing it with sand and clay and grinding the mixture to a fine powder. This powder then passes through a rotary kiln where it is heated to about 2600 degrees Fahrenheit, melting it and transforming it into a glassy rock called clinker. The clinker is mixed with a small amount of gypsum and ground to the consistency of face powder to produce the final product, Portland cement. The gypsum is used to control the speed that the cement solidifies once the water is mixed with it. Then the finished cement goes to storage facilities from which it is shipped out to users. This photo at the Holnum Cement Company in Mason City shows their rotary kiln. The hot gases that melt the limestone mixture to produce the clinker move up through the kiln and eventually to the smokestack. The limestone mixture moves down through the kiln, moved by gravity, until the clinker emerges at the far end. Following the Devonian, the Mississippian period, between about 358 and 325 million years ago, continued the deposition of fossiliferous limestones in Iowa, but also included some shales and sandstones. The Mississippian is named for the numerous exposures of rocks of that age along the Mississippi River Valley between St. Louis and southeast Iowa. The period is often referred to as the Age of Crinoids because of the proliferation and marvelous preservation of these animals in Mississippian rocks. This diorama shows a variety of species of crinoid and fishes that inhabited the Mississippian seas that covered Iowa. The Mississippian landscape was becoming very crowded with plants and animals. Insects evolved wings and diversified greatly. Tetrapods expanded across the watery landscape, and amphibians began to live on land. As Iowa drifted closer to the equator, the hot, damp environment allowed vegetation to flourish, with ferns, scale trees, cycads, and horsetails expanding, and one group of plants evolved that produced thick-bodied trees that grew up to 20 feet in height in Iowa's marshes. Fossilized pieces of Mississippian plants, like this stigmaria, a piece of the root of the lycopsid tree, can be found in upper Mississippian sandstones in Iowa. In fact, plants were so abundant that their photosynthesis produced enormous amounts of oxygen and increased the oxygen concentrations at that time to as much as 30 to 35%, compared to the 21% of oxygen in the air today. Some of Iowa's most spectacular fossils were found at this Mississippian quarry, here being visited by a geology field trip. This is a Heimstra quarry in northwest Keokuk County, where the oldest known tetrapods in North America were found. These were among the first of the vertebrates to venture from the oceans and onto the land. The sketch of the tetrapod skull shown on the front cover of this guidebook is one of these spectacular finds. The animal is named Wachiria deltiae after the nearby towns of Wachir and Delta. This fossil specimen, from which the sketch was drawn, is now on display at the Field Museum in Chicago. It is one of several species of tetrapod, fish, and other animals that were excavated by geologists from the Field Museum, Iowa Geological Survey, University in Iowa, and others during the National Geographic sponsored excavations in 1986 and 1988. The Mississippian is known as the Age of Crinoids, and there was no shortage of these animals in the Mississippian seas of Iowa. Although they are still alive in today's oceans, they are much less widespread than they were in the Middle Paleozoic. These animals, sometimes referred to as sea lilies because of their flower-like appearance, enclose the main portions of their body in a calyx protected by calcium carbonate plates, connected to the seafloor by a column of disc or bead-like plates that attach to a series of root-like holdfasts. A series of calcium carbonate discs form flexible arms on top of the calyx that can move to direct food particles down into the mouth. Crinoids typically disarticulate into a pile of discs and short stem segments shortly after death, and that's how they're usually found in sedimentary rocks, like this one. However, under some conditions, they can be buried alive by storm-generated mud flows and can be preserved in exquisite detail, such as those found at the LeGrand Quarry in Marshall County. When these slabs are meticulously cleaned to remove the matrix around the fossils, they can produce some amazing specimens, like these from LeGrand that are from the collection of the Iowa State Historical Museum. Here's a close-up that shows some of the intricate details that were preserved when they were buried 350 million years ago. Starfish, a relative of the crinoid, were also found preserved at the LeGrand quarry. Another treasure that comes from Mississippian rocks are geodes, Iowa's state rock. Some of the best geodes, like those pictured here, are found in southeast Iowa and adjoining areas of Illinois and Missouri. They come in a variety of sizes and can be found with any of about 32 different minerals inside. The geode in the lower right is about 18 inches in diameter and contains 10 different minerals or variety of minerals. Most Iowa geodes are found around the city of Keokuk and are frequently referred to as Keokuk geodes. They are found in the Warsaw and Keokuk formations near the middle of the Iowa-Mississippian stratigraphic section. Geodes begin as a nodule of gypsum that forms at the bottom of the Mississippian Sea. The gypsum nodule is buried in limestone or shale, then groundwater slowly dissolves the outer layer of the gypsum, replacing it with a layer of very hard, fine-grained quartz known as chalcedony. Over time, the rest of the gypsum nodule is dissolved, leaving a void where a variety of other crystals can grow. This road cut in eastern Lee County in Iowa, not too far from Keokuk, exposes the geode-bearing portions of the Keokuk limestone and overlying Warsaw shale. This is a closer view of the geodes in the Warsaw shale at the road cut from the previous photo. These geodes typically weather out of the rock and are found in nearby streams. The dark blue color on the bedrock geologic map of Iowa shows the Mississippian outcrop belt, where rocks of this age are present at the bedrock surface. Mississippian rocks are exposed in numerous parks and recreation areas along their outcrop belt. This includes Stars Cave Park and Preserve in Des Moines County and Crapo City Park in Burlington. Mississippian limestones are also extensively quarried for aggregate, roadstone, agricultural lime, and many other uses. The next younger period is the Pennsylvanian, known as the Age of Plants, between about 325 and 299 million years ago. This was a period when the seas were constantly expanding out over the land and then retreating. With Iowa sitting directly on the equator, the extensive shoreline swamps provided an excellent environment for the growth of forests and related vegetations, which led to the production of many layers of coal. As discussed earlier, the last supercontinent, Pangaea, was assembled in the Pennsylvanian. Conditions at that time were right for the buildup of a large glacial ice cap on the South Pole as Pangaea came together. As the glaciers grew, sea level dropped, and the seas withdrew from Iowa. Then, when the glaciers began to melt, the sea level rose again, and the seas again transgressed into Iowa, as can be seen on this map. This cycle of glacial growth and the seas retreating from the state, followed by glacial melting and the seas returning, was repeated about 100 times during the Pennsylvanian. As the seas moved out over the landscape, they brought with them a variety of depositional environments. In the deeper water, farthest away from shore, circulation was poor and the organic material that sank to the bottom decayed, using up all of the oxygen and creating an anoxic environment that very few animals could survive in. Deposition was very slow, with only the finest dust and clay particles settling to the bottom. In this environment, black shale was formed. A little closer to shore, the water was shallower, circulation was a little better, so some life forms could exist. However, the water was still too deep for sunlight to penetrate to the seafloor, so few animals lived there, and principal rock unit deposited in this environment was a gray shale. As we move closer yet to the land, into a shallower water environment, sunlight could reach the seafloor, so corals and other limestone producing animals could survive. Limestone was deposited in this region. And finally, closest to shore, the water was shallow and hot. Rivers continuously dumped sand and mud into the sea, so animal life was again limited. In this region, sandstone and claystone formed, and vegetation grew in the lowland swamps, producing coal. This sequence of depositional environments moved onto the land as the South Pole glaciers melted and the sea levels rose, what geologists call a transgression. If we were to watch one area, as indicated by this red rectangle, we could observe this sequence of environments pass and the various rock types typical to each be deposited. We would begin with a shoreline environment with sandstone, mudstone, and coal. As the seas rose, limestone would be deposited, then gray shale, and finally black shale when the sea was the deepest. Then, as the seas retreated with the next buildup of glacial ice on the South Pole, what geologists call a regression, the same sequence of depositional environments would pass, depositing the same rock types in reverse order. This sequence of transgression and regressive deposits is known as a cyclothem, and it was repeated all or in part almost 100 times in Iowa. Consequently, geologists have had great difficulty identifying individual units. Through the years, they have utilized conodonts, those are the microscopic jaw apparatus of marine worms that evolved very rapidly, to differentiate between the marine units from the different cyclothems, and pollen grains from plants to differentiate between the terrestrial units. Pennsylvania coal was a valuable resource for Iowa in the early 1900s. Coal formation begins with dense vegetation growing in coastal swamps. As these plants die, they begin to decay, depleting most of the oxygen in the water and building up a thick mat of vegetation, or peat, on the swamp floor. Its partial decomposition supports new plants that grow on it, and the slowly rising sea allows the peat layer to grow thick. Let's say this peat mat reaches 50 feet in thickness. The peat is about 60% carbon, and it can be mined and burned, producing about 5.5 million calories per kilogram. The coal swamp is eventually overwhelmed by the influx of sediments and is buried by sand, shale, limestone, and other types of sediments. The weight of all these sediments compresses the 50 feet of peat into about 10 feet of low-grade coal called lignite. This lignite is now 70% carbon and contains about 6.5 million calories of energy per kilogram. Deeper sediment burial further compresses the 10 feet of lignite to about 5 feet of bituminous coal with an energy value of about 7.8 million calories per kilogram. This is the rank of the coal that was formed and mined in Iowa. In other areas, such as the Appalachian Mountains of West Virginia and Pennsylvania, the bituminous coal has been metamorphosed, further compressed and deformed as mountains were pushed up by colliding continents. The 4 feet of anthracite coal that is formed by the metamorphism of 5 feet of bituminous coal is now about 95% carbon and has an energy value of about 8.6 million calories per kilogram. Pennsylvanian rocks are at the bedrock surface in the areas colored light blue on the bedrock geologic map of Iowa. This includes most of the southern and central part of Iowa and a number of scattered locations in the eastern half of the state. A mineable thickness of coal, that is, greater than 26 inches, is present on the areas colored blue and lavender on this map. The black dots identify at least 3,000 known coal mines. Of course, the dots are much bigger than the actual mined area. And the red lines outline the counties in which coal was produced. Most of the coal was mined from the Cherokee group, colored light blue, and the Marmaton group, colored darker blue. Some coal was also mined from the upper part of the Pennsylvanian rocks in Iowa, the Wabaunsee group, colored lavender. This graph shows Iowa's total coal production between 1860 and 1940. The year of peak production was 1917, when Iowa produced 9 million tons and led the nation's states in coal production. 10 counties in south central Iowa, shown in orange, had the greatest percentage of Iowa's coal production. The 10 counties and their total coal outputs between 1840 and 1994 are shown on the chart on the left. The total production of these 10 counties was over 333 million tons, about 93% of Iowa's historic coal production of 359 million tons. This seems like a lot of coal, until it's compared to the 1 billion tons of coal produced in the total U.S. in 2012 only. The coal that has been mined in Iowa is only a small fraction of the coal that still remains in the ground. If we look again at the 10 largest producing counties, it was estimated that their Pennsylvanian rocks originally contained over 3.9 billion tons of coal in beds of thicknesses of 26 inches or greater. About 1.7 billion tons was close enough to the land surface that it could be extracted by strip mining. So far, only about 20% of the coal that could be strip mined has been removed, and including underground mining, only about 8% of the total mineable coal has been extracted. That means that these 10 counties alone have over 3.6 billion tons of mineable coal remaining in the ground, and 1.3 billion tons of that could be stripped. In 2013, Illinois Basin coal was valued at about $45 per ton. That makes the total value of mineable coal in these 10 counties about $164 billion, and the value of strip mineable coal about $58.5 billion. The coal beds in Iowa are not as thick as those in the Illinois basins and the western states. Consequently, they can't be mined as efficiently. Additionally, Iowa coal is often higher in sulfur, usually requiring scrubbers to remove the sulfur from the smokestack gases to be legally burned. Therefore, coal has not been mined in Iowa since the American Coal Company closed its operation in Marion County in 1994. The Pennsylvanian rocks in Iowa also include sandstones deposited in rivers that were flowing across the state on their way to the sea. These sandstones can be seen in a number of places around Iowa, specifically the southern part of the state, including Wildcat Den State Park in Muscatine County and the Whitebreast Recreation Area along Lake Red Rock in Marion County. Pennsylvania sandstones have also been mined for building stones, perhaps most prominently many of the old buildings in the Amana colonies of Iowa County. Pennsylvanian shales were mined over much of its outcrop belt for use in making bricks, sewer and agricultural drainage tiles, and other ceramics. But now most of these facilities are closed and only one commercial quarry and brick production plant remains today. Pennsylvanian limestone is still widely quarried throughout the area, including here at the Thayer Quarry in Union County. The last of the Paleozoic periods is the Permian, between about 290 and 251 million years ago. The Permian is known as the Great Dying because it ended with the greatest known extinction of life forms in Earth's history. By the beginning of the Permian, all of the Earth's continents had merged to form a single supercontinent named Pangaea. After a few initial transgressions of the sea into western Iowa, the state became landlocked and subject to deep erosion. Permian sediments and some of the older rock section in Iowa were eroded during the Permian. This chart shows a number of families of life forms that were alive on Earth at any time from the Precambrian V to today. The chart at the left shows a classification of life forms with increasing number of subdivisions as you move up, and families are near the top. The black line shows the number of families that were alive at any given time grew into the Ordovician, then remained relatively constant with a few precipitous drops indicating extinction events. Then, at the end of the Permian, the Earth's greatest known extinction event killed off over half of the families of life forms. We can get a better idea of the extent of the end Permian extinction if we look at a more detailed subdivision of life, the species. At the end of the Permian, about 95% of all of the species of plants and animals living in the oceans became extinct, and about 70% of everything alive on land. This extinction was probably the product of a number of events, including massive volcanic eruptions and a large meteor impact. It marked the end of the Paleozoic eon and set the stage for the evolution of the dinosaurs in the Mesozoic. This completes our review of the Paleozoic era of the geologic history of Iowa. It was prepared by the Iowa Geological and Water Survey with assistance from the Iowa Limestone Producers Association.